Now this one gets a little bit more heavy. We up the tempo somewhat on this. We arrive at cyclotron motion, where a uniform electric field here it has an effect on positive and negative charges, like so, where positive charge would go toward along with the electric field and negative against. These are the parabolic paths of charged particles in a uniform electric field. Now we're going to go straight on to a magnetic field here. It's just a bit more interesting. I'll tell you why in the end. Right, we take from Lorentz force law here, where the electric field is zero, so we get the equation of motion by Newton's law, F equals ma here, where this is the magnetic component of Lorentz force law. So acceleration due to the magnetic field is given here. Now, choosing Cartesian coordinates with z-axis in the direction of the magnetic field, the vector product is this. So the components of acceleration are here. The differential equations involving v of x and v are coupled. Now we take a second derivative with respect to time and substitute our dv of y with respect to time and dv of x with respect to time, and we obtain these equations here. Now these solutions were both vx and vy were sinusoidally with time, move sinusoidally with time, with angular frequency the charge multiplied by the magnetic field over m, which is the mass. This means Vx and Vy will oscillate smoothly according to a sine wave. The general solution of these equations is here. We note that Vx we know that Vx squared plus Vy squared equals V perpendicular squared. So the V perpendicular represents a constant speed in a plane perpendicular to the field. Vz equals V parallel. Now, which is constant. So V squared equals Vx squared plus Vy squared plus Vz squared. This particle's kinetic energy is constant, as you'd expect when we're neglecting the electric field. The constant here, psi, is a phase that depends on the initial conditions. Now integrating the equation 1 here, where x of 0, y of 0 and z of 0 are constants of integration, and xy components represent uniform circular motion in a plane perpendicular to the field. This motion is centered on x0 and y0, and its angular frequency is given here. No, motion in direction parallel to the magnetic field is not affected by the magnetic field. This is the path of a charged particle in 3 dimensions, and it describes a helix. When viewed along direction in which the field vector points, positively charged particles are deflected in anti-clockwise direction and negative in a clockwise direction. The angular frequency of a charged particle's circular motion in a magnetic field is known as the cyclotron frequency, given here. The period corresponding to the frequency is called the cyclotron period, Tc, given here, and the radius of the circular orbit is given here. Now what makes this really interesting is because this is really important when it comes to particle physics, like CERN, the particle accelerator. People that work on that, you would notice with this equation the radius here is dependent on the mass, and the way the particle moves, the direction is dependent on the charge as well, along with the magnetic field. So the physicists at the Large Hadron Collider can determine the charge by the direction in which the particle moves, and also the mass by the size of the radius, the cyclotron radius here, because as we see, it's dependent on mass. So this is quite a crucial concept if you want to determine the mass of fundamental particles and their charge. And aside from that, I believe it has medical applications and applications in electronics, applications in all areas of electronics. And that's wrapping up for now. Please do subscribe if you want to see more videos like these. Thank you.